video, we'll be proving that the determinant of a lower or upper triangular matrix is the product of the entries on the main diagonal. First, recall what is lower or upper triangular matrix. It is said to be that a square matrix is upper triangular when it has all zero entries below its main diagonal, and it is said that it is a lower triangular when it has all zero entries above its main diagonal. We can show a lot of examples to show that this statement is true. But we have to remember that an example alone is not a proof. However, it often guides our proof. We can use examples as basis to construct our proof. Moving forward to our formal proof, let's claim that the given statement is true, that the determinant of an upper or lower triangular matrix is the product of its main diagonal entries. We will show basis for that claim. We will show that our claim is true for upper or lower triangular matrix A of orders 1, 2, and 3. So observe, if we have matrix A of order 1, our matrix is equal to this matrix. If our A is equal to this matrix with only one entry, and the determinant of our matrix is the only entry itself. Observe, if we have a 2 by 2 matrix A, then our A is equal to this matrix A, B, 0, D, and its determinant is the product of A times D. Another example. Observe that if we have a 3 by 3 upper triangle matrix A, then A is equal to this matrix A, B, C, 0, E, F, 0, 0, I. And to get the determinant, it is always best known to work with a row or column that has a bunch of zeros. In this example, our matrix A has its first column with bunch of zeros. So the first column, we will work that first column. And if we will expand using Laplace expansion, our first column will get, if we will get the determinant of our matrix, then we'll get the first entry multiplied to its minor, the submatrix, and minus 0, the second entry in that column, multiplied to its minor, plus the third entry in that column multiplied to its minor. And basically, as you can observe that since we have here the multipliers 0, then the product of that, even if its number is this, is always 0. So that will just be cancelled out. And we are only left with the product of this, the first entry with it, and its minor. So the determinant is the product of A times the product of this. So the product, since that this, if we multiply these two entries, this will give us 0. So only the product of this A times E times I will give us the determinant of our matrix. So as you can see, this product is actually the main diagonal of our matrix, a 3 by 3 upper triangle matrix A. Similarly, if we will work with our lower triangle matrix, we have everything above and above our main diagonal zeros. So if we will expand our first row, since it has a bunch of zeros, we'll just deal with our first entry. If we'll expand that, we'll get the same. This will just be cancelled because this is we have multipliers 0. So we'll also get the product of uh, the product of its main diagonal, which is A times E times I. After observing the basis for our claim, let's generalize our proof. So assume that our claim is true, then we will show that it is also true for every upper or lower triangular matrix A of order n. Take note that it's a matrix A of order n, and we'll use an upper triangular to show this, and we'll just have to expand repeatedly the first column. Let's say we have this matrix A with entries A11, A1, E22, A33, goes the main diagonal goes to A and A sub n, and the first row we have the A11 goes to A1n, and everything under the main diagonal are zeros. So it's easier to work the first column to get the determinant of our matrix A. So to get the determinant of that matrix, we will get the product of the the first entry multiplied to its submatrix, which is submatrix, which is if we will get the minor, then we'll just have this A22 in the first row goes to A2n, and in the main diagonal we have A22 goes to A sub n, and everything under the main diagonal is zeros. So we have another situation here that these are zeros again, so we'll just work with our first row. So don't forget that we have this A11, and in the next slide, so from here, if we want to get again um, the determinant of our matrix, we'll just multiply the A11, A22, and multiply to its submatrix, which is that from here the A3, it should be A33. Okay, A33 and goes to A sub nn, and in the first row it should goes to it should be 3 A sub 3n, and everything under our main diagonal are zeros. So that will just go on, keep going with that up to A and n. So as you can see that the determinant of our matrix, as you can observe and see the pattern, it will just give us that it is the product of A11, A22, A23 go A33, it should be A33 goes to A sub n minus 2, n minus 2 multiplied to the 2 by 2 matrix A sub n minus 1, n minus 1, and n minus 1 n 0 here, and goes to n n a and n. And as you can see, the product of this is just 0. If you multiply this to entries, the product is 0. And if you multiply this to this, that will just give us a and n. So now we get the determinant of our matrix A. It is the product of A11, A22, A33 goes to A and n, and which is basically just the product of its main diagonal on the upper matrix. Uh, you can verify that. And here, similarly, if we will show the lower triangle matrix by expanding the first row repeatedly, we will also get the same determinant. So um, from our claim, from our proof, we can generalize that. Hence, based on the result, we can conclude indeed the determinant of an upper or lower triangle matrix is the product of its main diagonal entries, and we just prove the statement.